So, have you ever just stopped, looked around, and wondered, what is the universe actually made of? I mean, at its most fundamental bedrock level, what are the literal building blocks of reality? Well, today we are opening up the ultimate cosmic recipe book to answer exactly that question. Welcome to this explainer. Together, we're going to decode the master recipe for everything around us. It's a framework known as the Standard Model of Particle Physics. Now, this is arguably one of the most wildly successful scientific theories ever created by humanity. And today, we're going to break it down so you can truly grasp how our universe operates at the quantum level. All right, here is our roadmap for today. We'll start with what the model actually is, move into fermions and bosons, explore the famous Higgs mechanism, and finally look at the unexplored mysteries. Let's jump right in. Starting off with section 1, what is the model? Think of it as the ultimate cosmic recipe. You know, this isn't just some dusty, abstract academic chart hanging on a laboratory wall. It's a comprehensive, highly tested physical framework. As theoretical physicist Gordon Kane puts it, it is literally the most sophisticated mathematical theory in history. And honestly, he hit the nail on the head. It identifies the basic, indivisible particles of our universe and specifies exactly how they interact. Essentially, everything that happens in our world, with the notable exception of gravity, happens because these tiny particles are following the precise rules laid out in this very model. Moving right along to section 2, fermions, the ingredients of reality. To really get this, we have to draw a clear line in the sand. In the Standard Model, everything is divided into two distinct camps, fermions and bosons. Think of it like this. If the universe is a giant cake, fermions are the flour and the sugar. They are the actual physical ingredients. Fermions have a half-integer spin, they form all matter, and crucially, they obey the Pauli exclusion principle. Basically, that just means no two identical fermions can occupy the exact same quantum state at the same time. They actually take up physical space. Bosons, on the other hand, have an integer spin. They don't make up matter at all. Instead, they transmit the forces between matter. And since they don't obey the Pauli principle, they can just pile up infinitely in the exact same spot. Okay, so how are these fermion ingredients actually organized? Well, they fall perfectly into 3 distinct generations, giving us exactly 12 fundamental matter particles. First, we've got 6 quarks: up, down, charm, strange, top, and bottom. Quarks love to be tightly bound together to form larger things like protons and neutrons. Then we have 6 leptons. This group includes the superfamiliar electron, its much heavier cousins the muon and the tau, and their corresponding, almost ghost-like neutrinos. But here's the fascinating part. Almost all the normal stable matter in your body and the entire world around you is made purely from just that first generation: up quarks, down quarks, and electrons. Why? Because the heavier generations decay incredibly fast right back into that first tier. Which brings us to section 3, bosons, the messengers of the universe. So we've got our ingredients, right? Now let's look at the forces. If fermions are the ingredients, bosons are the binding agents. They're the messengers that dictate exactly how our fermion ingredients are allowed to talk to each other. Now, there are 4 fundamental forces in nature. And in the quantum world, forces are transmitted by tossing these boson particles back and forth. Photons carry the electromagnetic force. They're what keep electrons tied to atoms. Gluons, they are the messengers of the strong nuclear force, basically acting like superglue that powerfully binds quarks together. Then you have the W and Z bosons, which mediate the weak force. That's the one responsible for things like radioactive decay. And finally, there's the graviton. This is the theoretical carrier of gravity, which, spoiler alert, is completely missing from the Standard Model right now. Now, I want you to consider this quote. The vacuum is not empty. I mean, that sounds like a total paradox, doesn't it? It completely shatters our everyday understanding of what empty space actually is. Because in classical physics, a vacuum is just a dead, empty void. But the Standard Model, it tells a wildly different story. And that brings us to virtual particles. You see, the quantum vacuum is actually this chaotic, boiling soup. Thanks to the weird rules of quantum mechanics, particles and antiparticles are constantly popping in and out of existence, everywhere, all the time. They borrow energy from the vacuum for an unbelievably brief fraction of a second just to transmit forces. And then boom, they vanish. They are the fleeting, unseen messengers of reality. Which leads into one of my absolute favorite concepts, the naked versus dressed particle. So imagine a bare, theoretical electron, a naked particle. Because the vacuum around it is boiling with those virtual pairs we just talked about, this negative electron attracts a bubbling cloud of virtual positive positrons all around it. That cloud acts like a literal shield. So the physical electron we actually measure in a lab, the dressed electron, has its electrical charge partially shielded by this vacuum polarization. It's only when physicists smash particles together at absolutely extreme energies, piercing right through that cloud, that we finally see the true higher charge of the naked particle inside. All right, section 4, the Higgs mechanism. This is the secret sauce. So up until the 1960s, the mathematics of the Standard Model were looking absolutely beautiful. But there was a massive, glaring flaw. The math flat out demanded that force-carrying particles, like the W and Z bosons, have absolutely zero mass. But real-world physical experiments proved they were actually quite heavy. To solve this major paradox, physicists proposed the Higgs mechanism. Picture an empty room. This represents the invisible, omnipresent Higgs field that completely permeates all of space. When a fundamental particle enters this space and tries to move through it, it interacts with the field. This interaction creates a sort of cosmic drag. And that drag is exactly what we measure as physical mass. Light particles, like photons, don't interact with the field at all, so they just fly through at the speed of light with zero mass. But heavier particles have to wade through it, acquiring their mass much like a famous celebrity trying to push through a crowded party, gathering this massive entourage that just slows them down. And the best part? This wasn't just some elegant mathematical trick. In 2013, scientists at the Large Hadron Collider at CERN finally confirmed this massive theory. By smashing protons together at unimaginable speeds, they excited that invisible Higgs field just enough to knock loose its physical manifestation, the incredibly elusive Higgs boson. It was this absolute monumental triumph that finally completed the core of the Standard Model. Which brings us to our final section, Section 5, the unexplored mysteries, the missing pages of our recipe book. Because look, despite all this incredible Nobel Prize-winning success, I have a pretty jaw-dropping reality check for you. This entire beautiful framework we've just spent our time exploring, which accounts for every star, every planet, every galaxy, and every single human being, only makes up roughly a tiny 5% slice of the cosmos. That's it. The other 95%? Completely unknown. It's made up of dark matter, which is invisibly holding galaxies together, and dark energy, which is somehow accelerating the expansion of the universe. And the Standard Model explains absolutely none of it. So what are these massive missing pages physicists are still pulling their hair out over? Well, first off, gravity is completely missing. We still have zero quantum theory for it. Second, the universe is full of matter, but almost no antimatter. Why? The math says they should have been created in perfectly equal amounts. Third, we recently figured out that neutrinos actually oscillate and change flavors mid-flight. That completely proves they have a tiny bit of mass, which is something the original Standard Model insisted was impossible. And finally, what particle actually makes up dark matter? Could it be some completely undiscovered heavy particle out there, like the theoretical neutralino? And the mysteries just keep piling up. Take the very recent muon G2 anomaly over at Formulab. They put muons into this giant magnetic ring, and the particles wobbled. But the crazy thing is, they wobbled significantly faster than the incredibly precise predictions of the Standard Model allow. That unexpected wobble heavily hints at physics existing completely beyond our current understanding. Which leaves us staring at a pretty massive, provocative question. Is there a fifth force of nature out there? Are there undiscovered phantom particles interacting with those muons deep in the quantum vacuum? The Standard Model is undoubtedly the greatest scientific recipe book ever written by humanity. But the next time you look up at the night sky, just remember, we are really only just beginning to figure out the ingredients. Thank you so much for joining me on this explainer, and I hope this sparked your curiosity to go out and learn even more.